Hello, I'm Dr. Matthew Jones. I'm an environmental analytical chemist currently working in the Wolfson Atmospheric Chemistry Laboratory at the University of York in the United Kingdom. My short talk today, entitled A Clean Ocean, Nature's Advanced Oxidation Processes, will introduce how there is a balance in marine and atmospheric systems as they interact to essentially produce a self-cleansing system. Advanced oxidation processes is a term coined by chemical engineers for a large suite of reactions used during drinking and wastewater treatment. Reactions typically involve a strong oxidant with and without UV light acting on harmful substrates, for example, toxic bacteria or organic and inorganic pollutants. However, these processes are only echoes of what occur in nature. Many of these processes are studied in the atmospheric sciences and microbial and molecular biology. Atmospheric chemists have shown how advanced oxidation processes are essential in the environment and affect redox-sensitive species, while microbial and molecular biologists understand these processes in terms of organic material recycling and detoxification of reactive oxygen and nitrogen species. While what we can suppose is that over billions of years, any marine biota has evolved to harness the effects or conversely nullify advanced oxidation processes. Why? Because in and around shallow marine systems, UV light is present, and so too are the oxidants ozone, hydrogen peroxide, manganese oxide, and nitrite. This supposition suggests that there is a positive yet balanced outcome for microbiology and their oceanic environment. Of all the marine environments, there is one that is optimized towards advanced oxidation processes. This is the sea surface microlayer. The microlayer is the marine environment that we know the least about. Though it is the most accessible, it is also one of the hardest to sample, making it an excellent choice for laboratory studies. The microlayer is the ocean-atmosphere interface, and as an interface it controls feedback processes. The organic-rich nature of the microlayer means it has a unique reflective property. The layer is also a source of particulate aerosols, while simultaneously disrupting gas transfer fluxes into and out of the ocean. Importantly, reactions therein have consequences that can be traced both deeper into the marine environment and back into the atmosphere itself. One process controlled by the sea surface microlayer is the removal of lower atmosphere ozone. This removal process has significant feedbacks to both the atmosphere and the marine environments. Reactions of lower atmosphere ozone at the surface microlayer produce strong climate feedback. Ozone will react with iodide and through a reactive intermediate species, hypoiodous acid, or HOI, produce volatile iodine species that are cloud condensation nuclei, hence the climate feedback. This reaction also reduces any harmful lower atmosphere ozone concentration and provides a source of the essential human nutrient iodine. However, the reaction of ozone also releases a cascade of reactive oxygen species into the marine environment. Reactive oxygen species including hydrogen peroxide. This cascade of reactive oxygen species leads to a range of advanced oxidation processes. The ozone-iodide reaction is a balanced self-cleansing ocean process, but it is likely this balance is shifting. Ozone uptake by iodide is inhibited by the buildup of anthropogenic surface active molecules unreactive to ozone, those such as polyfluorinated alkyl substances or sodium lauryl sulfate. Atmospheric nutrient deposition acts to increase the marine biomass, but this increase results in extra organic material fluxing to the surface microlayer, and this provides competition for iodide towards the ozone, while the addition of reactive chemical species disrupts the reactive oxygen species cascade through the marine environment. The atmosphere marine environment has an ability to self-cleanse, but as we overload the system, the benefits of this self-cleaning balance are removed. The results are that the availability of an essential human nutrient decreases. The oceans find it harder to check the spread of toxic and dangerous chemicals, and the likely effects of cloud formation may be huge, but it is yet unknown.